So for our next discussion here of cosmology, we will ask, how far can you see? Isaac Newton, a lot of theorists after him thought the universe was infinite. That raised the whole problem of Olber's paradox, as we explained. So that suggests maybe it wasn't infinite. And then finally, after the idea of after the discovery that the universe was expanding, after the Friedmann equation, the basic idea of the Big Bang, the universe had a beginning. So it was not infinite in age. That suggests it's not infinite in size. So can we see to the edge of the universe? And so this is actually an interesting question. What would the edge of the universe be? Because the universe is like all of space. So how can space have an edge? And so this gets into a question of the nature of space and nature of the universe. Turns out it doesn't actually have an edge. So, but what do we mean by all that? First of all, we have to define what's called the observable universe. Remember, the universe is finite in age, so the farther away that you look, the farther back in time you're looking. So if the universe is only 13.7 billion years old or thereabouts, that means that you can only see something 13.7 billion light years away. Beyond that, it would take longer than the age of the universe for light to even reach us. So that determines the edge of the universe. So even if the universe were bigger than what we could see, we can't see farther away than that. So if there were galaxies out there, we would never see the light of them because in the age of the universe, the light hadn't reached us. The farthest back we can see 13.7 billion light years. Well, that's about the age of the universe. So that means we're actually we would see at that point what's essentially close to the Big Bang. So that would be pretty much the origin of the universe. So that defines what we call the observable universe, defines what we call the light radius of the universe. And so, interesting thing though is that the universe might be 13.7 billion light years, the farthest we can see, but in the 13.7 billion years, the light's been traveling towards us from what we call the edge of the universe. That edge has moved out to 47 billion light years away. So the universe is way bigger than we can see simply because of the expansion. So what determines the rate of expansion? Well, rate of expansion is going to be determined by what's in the universe. So gravity, we would expect, would slow the rate of expansion of the universe. And what makes gravity? Mass makes gravity. And so mass makes gravity, but it makes a big difference how the mass is distributed. So we also have to be cognizant of the density of the universe. How concentrated is the mass? Again, we ran into this when we talked about stars and black holes. You can have a 10 solar mass star, but you cannot have a 10 solar mass white dwarf or a 10 solar mass neutron star. Something like that would collapse into a black hole. And so you have 10 solar masses, but if they concentrate it enough, it changes what it is. It's going to change into a black hole. So the density of the so if the universe is, and again, this is the graphic out of your book, and I don't know why they do this, but this is pretty much standard how they do it. They flip the axes. So instead of velocity on the y-axis is now distance on the x-axis. Instead of distance on the x-axis, the y-axis is now distance instead of distance being the x-axis, and velocity, which used to be in the y-axis, now the x-axis. So your book does this. I think it's dumb because the other graphs in the book have always been the other way around. But oh well, they didn't ask me. But the way we look at this is if you have lower density, so less gravity, that makes the universe expand faster. Higher density makes it expand slower. Well, the other thing we look at is when the basics of the Big Bang, things are getting further apart, the gravity's getting weaker. So that means gravity was stronger early in the universe than it is today. So if you look farther and farther away, you would see a slower expansion than you do today. And so That would be that would mean that the farther away you look, the Hubble constant is not really constant. It actually is going to vary. If the universe was totally empty and there's no mass in it, then the Hubble constant is in fact constant. It goes straight out. Well, obviously there's mass in the universe. We're here, okay, and we're here, and so we obviously there's mass, so it's not going to be that, and so what we're looking at is what would happen. So what they expected was that this is going to be curving a little bit, and how much it curves depends on how much mass of the universe. And so to measure that, and then that would be, we'd have to look at something really, really far away. Now, why care? Because that determines what happens in the future of the universe, is what they were thinking. And so what they were thinking was the future of the universe depends on how quickly it's expanding. For example, if there's so much mass in the universe, there's actually the possibility the universe could expand and reach a maximum expansion and then fall back in on itself. They call that the big crunch. We have the Big Bang, the big crunch, the entire universe falling back in on itself. Or the possibility is the universe could expand forever and gravity never slows it down, and just keeps expanding forever. And so that would correspond to a universe being a little bit less dense. Okay. And in between the two is a universe that expands critically. And that is, it expands, gravity slows it down, but gravity would pull it to a stop after an infinite amount of time. Well, the thing is that the difference between a gravity that's the universe that's critical density, subcritical or supercritical density, in other words, it expands forever or collapses at a big crunch, is incredibly tiny. Just 1 nanosecond after the universe, these enormous, there's not even a name for numbers that big, but that last digit is all that changes. I mean, this would correspond, for example, to something maybe in the entire universe, there's 1 electron extra or 1 electron missing, in the early universe, and determining whether we expand forever, whether we have enough gravity to expand forever, or whether we slow down. And the idea of this critical density, that's just unheard of. The likelihood of that would be like close to nothing. Because imagine imagine how much stuff is in the universe. Imagine 1 electron too many, 1 electron too few. What's the chance that we have exactly the right amount? Well, this would be like, you just on a lark buy a lottery ticket and win the lottery, and then you decide to take the winnings from that and buy 10 more lottery tickets, and you win 10 more lotteries. And then you decide, that, okay, you're done with this, you're not going to win anymore, and then an airplane crashes, and turns out that everybody on the airplane had a winning lottery ticket, and they all just blow around in the breeze and end up at your feet. I mean, that likelihood of that sort of thing happening is vastly more likely than the universe having exactly the critical amount of stuff in it. Okay, problem. Every measurement that they were making showed the exact critical amount of stuff. And so when I was in graduate school, 1980s into the 90s, these were the measurements that they were making, and it was like a total absolute shock, because the chance of it being that way was close to zero. And yet this is exactly what they were finding. And so this didn't seem to make any sense. And so they were saying, well, what does this mean? And turns out that this was a major area of research as to what does this mean. And it has to do with the curvature of space. Remember, gravity curves things. More gravity curves things more. Space is expanding and being curved. And so Einstein and Willem de Sitter worked out the parameters for expansion in the universe and the curvature of space. The first one they did was for an empty universe because that was make the math easier. Then they started working on what happened if the universe has stuff. And it finally comes down to just three numbers. We have something called the density parameter. Density parameter is a ratio of the density of the universe to the critical density. So that can be greater than 1 or less than 1. Equal to 1 means the universe is exactly critical density. Problem was, everywhere we looked, we kept seeing critical density. And that's highly unlikely. As I said, the probability of that's like close to 0. The curvature constant, that can be +1, 0, or -1. +1 would be what would happen if you were above critical density. -1 is what you'd have if it's below critical density. And 0 would be what you'd have if it is exactly equal to critical density. And the deceleration parameter is like half of the density parameter. Not a very significant thing. But this is what we come up with. And of course, what happens is, depending on what happens, what the density is, the curvature constant, then that would determine the age of the universe, whether it's equal to the Hubble constant, the Hubble time, shorter than Hubble time, longer, or whatever, and really it's about 2/3 of the Hubble time. And we talk about the geometry of the universe. We actually say if the universe is +1, it's spherical. If it's -1, it's hyperbolic. If it's equal to 0, that's flat. What do we mean by geometry of the universe? A spherical universe is closed. That means that it's going to eventually fall back in on itself, but it also means that if you go in a straight line, eventually you're going to end up where you started again. So it's closed. It's like the surface of the earth. It's not no edge to it. In a spherical universe, turns out that parallel lines will eventually come together, kind of like lines of longitude all meet. You're used to learning what we call Euclidean or plane geometry, and that's on a plane, on a flat surface, in which parallel lines never meet. If the curvature constant is less than 1, we call that hyperbolic space. And in hyperbolic space, the universe expands forever, and so eventually parallel lines, the space between is going to get bigger, and parallel lines will actually get farther apart. And so you can imagine something that's hyperbolic shaped being kind of like a saddle shape. And so this gives us the curvature of space. And so we have an open universe here. The open universe, spherical space is closed. Now, mathematically, a spherical space closed was really what they were thinking they wanted. A closed universe mathematically works out simple. Theoretically works out simple. We can talk about the universe having a beginning and an end, and all the mathematics really work well for that. Statistically, there's an infinite number of ways it can be open. There's nearly infinite number of ways it can be closed. One way it can be flat. Every measurement was coming up flat. Every measurement was coming up critical density. Every measurement showed that it came up flat. And this was like totally against anything the theorists were coming up with. And they couldn't figure out how that could happen. So to really measure this, the nature of the universe, they realized that what we needed was a telescope that could look super far away, did not have to worry about the Earth's atmosphere interfering with your observations. So it had to be a space telescope, a large space telescope that could see super far away to measure how the Hubble constant changes with time. And that's why they called that telescope the Hubble Space Telescope. And it was going to determine the curvature of the universe and what was going to happen, whether the universe was open or closed. The problem was it found something totally unexpected, and that's our next lecture.